Hello, everyone. This is Dr.Hira, and this discussion is about benzene and generally aromatic compounds. In this lecture, we'll talk about the structure of the benzene, especially, and how we can name the different analogs of the derivatives of the benzene under the IUPAC naming. Before discussing how to name the benzene ring or the aromatic compounds, we have to establish or have to be clear about some of the terms which are commonly used and technically in a wrong way. So the very first thing is we all know that, and commonly this is taken as an aromatic compounds, that the aromatic compounds are the benzene and its derivative. But more accurately, this aromatic term is not only limited to the benzene ring only. It is used to classify any compound that meets the Huckle criteria. Later in this lecture, we will discuss and we will see what the Hückel criteria is and what are the conditions that has to meet for a compound to be aromatic or not aromatic. For technically the right terminology for classifying the aromatic compounds, the benzene compounds, is the arene. So the term arene is used to describe aromatic hydrocarbons by analogy with alkane, alkene, and alkyne. And the benzene is the parent arene. This is a representative or the basic representative of this class, which is arene one. So just a group derived by removal of an hydrogen from an alkane, and we use the term as alkyl, and we represent it with R, and this dash is basically representing that it is in a bonding with something, with that could be any of the alkyl chain, aromatic, any of the functional group. So a group derived by removal of an hydrogen from an arene is called an aryl group. So if you have to mention specifically that this substitution or this link is between a benzene ring or an aromatic hydrocarbon, so then you will specifically write the AR bonding, and that is representing that this is not aliphatic, this is not the open chain, this is not the simple alkene alkynes. So this is something which is a closed ring, and that is the aromatic compound hydrocarbons. And this is basically the cyclic, the benzene ring, which is the closed ring structure. I will show you that how we draw the aromatic compounds on paper and even in some of the chemistry softwares when we are drawing the structures. So as the aromatic or the benzene ring, this is a six-membered ring and its molecular formula is C6H6. It means there is the six hydrogens are deficient if we just compare the equivalent of the cyclohexane compound. So there's that deficiency of the hydrogen one. So that deficiency is fulfilled by the double bond. So they are not a single double, they are the three double bonds, and they are in the alternative position. Alternative means that they are separated via one single double and then single double, single double. So in this alternative manner of the double bond arrangement, so these pi electrons are in constant movement. So they are not the localized pi electron bonds, they are the delocalized ones. So they keep on moving. So that's why sometimes just rather to draw every time for the three double bonds, we can easily draw this ring within that cyclic structure or cyclohexane to represent that these are there is the delocalization of the pi electrons. So that could you can use, and that these are the different versions how you wanted to make your drawing and the structure presentable. So even you can pick up the solid, the filled ring within that cyclic structure, and the dotted lines. So this is somehow giving you a little bit of its spatial arrangement with its stereo like these are the front bonds and that is on the back one, and it is inclined to that rotation, right? So otherwise, in a straight drawing, you can just draw that in that way, or otherwise with the three alternating double bonds. I will show you in the next slide. Now, the important thing is this one, that the structure of benzene. So the structure of benzene, as we see, and if we compare it with the previously discussed unsaturated hydrocarbons, we discussed the class alkenes and alkynes, and we have seen that this pi bond is very much vulnerable for the addition reaction with just a simple reaction conditions. If you are reacting this in the presence of light and some of the heat with the halogen or acid halide, so they go to the addition reaction. But that is not the case with the benzene. So we are not observing the simple addition reaction when we are reacting the benzene with any of the halogen. Why it's so? So that least reactivity, or not having the reactivity for the simple addition reaction like the alkenes and alkynes one, this is justified and explained by the two main theories. And these theories are basically the MO, and there is this is the molecular orbital theory, right? And the second one is the resonance theory, right? So that is somehow out of this discussion and this particular lecture. So I'm not going into that detailed one, but if you wanted to read more in detail that what the molecular orbital theory is explaining about the stability of this benzene ring and what is a resonance theory, so please, you are highly recommended to consult any of the organic textbook, and you can go for the organic chemistry by Brown and Foote, and there are a lot of other sources where you can just read about this one. So liberal text is also a very good online source you can refer to. So just at the moment, I wanted to explain this one, that the molecular orbital theory is also explaining that on the bonding and anti-bonding orbitals. So this benzene ring is basically at energy, and this is on the electronic configuration and orbital overlapping, that it is stabilizing its structure, and this is making it fully planar, that all of the p orbitals are in a good overlapping with each other. Secondly, in the resonance theory, there are more than 2 and 3 contributing structures of the benzene ring, which are stabilizing these one, and this is of the highest resonance energy, which is making this benzene ring resistant to most of the reagents, that they don't react with that one unless it is substituted with some of the species like the methyl, ethyl, or any of this one, that they can substitute. So the benzene ring is not giving you the addition reaction. It is rather preferred to go for the substitution reaction. So every time if you wanted to attach any of the substitution in a benzene ring, so there is a hydrogen on the benzene ring which has to substitute, and there will be the placement of that species, which, for example, in these reactions, if you just can look at it, so these are the halogen one. So here, if we react it with the bromine, so this is basically making this substitution reaction. So I just wanted to show you that what was the difference between the normal um, alkene and the benzene ring structure, right? So we are comparing these two. Sorry for if these are not joined, but obviously you have to draw that this carbon and carbon are closer linked, so there is no opening. So when we treat this any of the alkene with the halogen one, and this is the X2 or HX something. So here this is a bromine one. So what we get is that we got the haloalkane, right? And what would be the structure? So here we will get attachment of this bromine on the double bonding, and that is addition reaction. But that is not happening with the benzene ring. So when it goes to undergo this reaction, so there are the 5 hydrogen on each of that 6 hydrogen on each of that carbon in a simple benzene ring structure. So every time that hydrogen has to substitute with that one. So that's why if you just look at the molecular formula of this one, so you can see that there from the 6 hydrogen there is a 5 hydrogen, so that one hydrogen has removed, and then there was the benzene ring which can welcome the bromine substitution. So this is not going to the simple addition reaction, because it will go, if it will go to the addition reaction, so there will be the alkane and it will lost its aromaticity, and it will lost its original benzene ring structure. So the benzene ring structure itself is very resistant, and it is very much, you can say, the conservative or introvert, that it want to retain its identity. So the next is if you keep on reacting this mono-substituted bromobenzene with more halogen one in the presence of the iron FeCl3, iron chloride, or the ferric chloride, which is a catalyst. So here you can have the disubstituted benzene products out of it, but there are the 3 isomeristic forms which are possible. And now we have to see what are the 3 dibromo isomers are possible. So we can name that and we can explain that one. So take a moment and you can draw on your notebook just to test it, that one, that what are the 3 um, isomers which are the dibromobenzenes. So obviously one is already substituted, and then we are treating with more bromine. So the second will be attached on the different position. So that there is these 3 positions are possible, and this is the 2,1,2 dibromobenzene. This is the 1,3 dibromobenzene, and this is the 1,4 dibromobenzene. Later, we will talk about the ortho, meta, and para as well, right? So at the moment, we just wanted to discuss that this reaction will happen if we continue reacting with the more halogen. So there will be the further hydrogen which will be substituted, and there will be the second bromine which get attached to that one. So the next thing is, if we go to this, uh, now we have to talk about what's the Huckle criteria for aromaticity. So the Huckle criteria for aromaticity is summarized as follow. So for a compound, and it has set to be aromatic, it has to fulfill the these 4 points and these 4 basic criteria. So the very first thing is it has to be cyclic. The second thing is this, that there should be 2p orbital on each atom of the ring. That means, in normal way, that means this is a conjugation, because if there is no 2p orbitals of available for every atom, if you just look at on the benzene ring, so these both, all of the carbon have the one 2p orbital, and that is basically making this possible to move on that pi electron from this to this one, and this is facilitating for the overlapping. So that's why this is only possible when there is a conjugation. If there is no conjugation and there is no 2p orbitals, that is not possible for that one to accommodate these pi electrons in their capacity, and for the better overlapping of this one. So be planar or nearly planar, so that there is continuously or nearly continuous overlap of all the 2p orbitals of the ring. Now, the fourth one is another very important point is that it has to fulfill and it has to satisfy this 4n plus 2 pi electron criteria in the cyclic arrangement of 2p orbitals. So where n is a positive integer. So you have to put in that value and have to see and have to conform with your given structure that either that is satisfying these number of pi electrons by putting any of the value from these positive integers, then that will be an aromatic one. And now we will compare the two examples here just to make it understandable for you. And here, critically, you can evaluate these both examples. The one example is the benzene, and what the IUPAC name of the benzene is basically, this is the this is the 1,3,5 cyclohexatriene. And here you can see this is the cyclooctatetraene, right? Again, there is a 1, 3, and 5, and the 7 tetraene, right? So we have to see which one is the aromatic one and why it's so, and which one is not fulfilling the aromatic criteria. So let's check firstly the benzene ring, and here you can see this one, that there are the 6 membered ring, and this is a closed ring. So the first criteria is it should be cyclic. So this is cyclic one. The second one is that there should be the conjugation and every atom has a 2p orbital. So that is again is there. So this is in a continuous conjugation and every carbon has the 2p orbital with that. Now, the third one is that this is a planar one, and there is the face-to-face and the continuous overlap of these orbitals. Do remember, so there are a number of things which you have to explore and have to read a little bit more in detail about some of the geometries of and the molecular shapes of the structures. So when we talk about the ring structures, so the 6-membered and the 5-membered ring is a very stable ring shape because it is managing its ring strain to that level that this is not pushing and this is not disturbing the ring structure. While when you go for the smaller rings, like this is the 4-member and the 3-member, so they have the high degree of strain, ring strain. So that is making it unstable. So sometimes we will see in the next slides that either they are fulfilling the rest of the criteria, but due to their instability in the ring structure, they cannot accommodate. So they are basically deteriorating from their planar shape. So there are no more planar. So that's why they are not exactly the non-aromatic, but they term as the anti-aromatic. I will explain that one another example. So now if we just check for the benzene, so this is fulfilling the all of the three conditions. And now we have to see that either that is fulfilling the fourth condition or not. Now you just count these pi electrons. So these are the 2, 4, and the 6. So you know one bond means they are the 2 pi electrons. So you can see if we put the 1 in this value, so there's a 4 multiplied by 1 plus 2. So the overall value will get the 6. So it means this is fulfilling this 4n plus 2 pi electron, and that is the Huckle criteria. So it means that aromatic is justifying all of these 4 conditions, and this is the aromatic one. So that's why I have written there AR, right? Now we will see the cyclooctatetraene. This is cyclic. Every atom has the 2p orbital, and this is in a conjugation. The third one is it is in a planar and it's in a very proper equal bond distance to each other. Now the fourth one is if you just look at the pi electrons, how many 2 to pi electrons it has. So it has the 2, 4, 6, and 7, 8, and the 8 doesn't exist in this 4n plus 2 if we are putting this any of the integer value. So it means this is not fulfilling the zero point 0.4. So it means this is the non-aromatic compounds. Though overall, if you are viewing this one, this is as having the conjugation, this is cyclic, this is planar one, but this is not fulfilling the 4n plus 2. So on the basis of all these 4 points, you have to check that either the given compound is the aromatic or it is not aromatic, right? Now, the next thing is, as I have mentioned, that there is a term anti-aromatic hydrocarbons. So a monocyclic compound that is planar or nearly so has 1 2p orbitals on each atom of the ring and has 4n pi electrons in the cyclic arrangement of overlapping 2p orbitals where n is an integer. So anti-aromatic compounds are especially the unstable. So if you have to classify them from the aromatic and non-aromatic, so they comes as aromatic one, but they are not showing the proper aromaticity because they are unstable. So that's why another term we use for these one is the anti-aromatic or anti-aromatic. So here we are comparing the example of the cyclobutadiene, which you will classify as aromatic if you are categorizing on the basis of aromatic versus non-aromatic. But this is not the true aromatic compound. Why? Because though this is cyclic, this is the planar one. It has the 4 pi electrons, which you can see if we putting 0 here, so this is the um, you can see that this is fulfilling this one. So there is no place for the 4 electrons, right? So here you can see this is simply that this is not fulfilling the 4n plus 2 electron criteria. But some compounds, if they do fulfill all of that criteria, so they are even then are not in the aromatic class because they are the unstable ones. So cyclobutadiene is not stable because its actual shape is not this equally distant square form. This is the rectangular because there are the pi electrons, but they are distant because of the smaller ring size. They get distance to manage their ring strength. So that's why we term it as the anti-aromatic hydrocarbon. So here you can see next one is the nomenclature. So for the nomenclature, what we have to see is there are the 3 categories how we can name these ones. So there is a monosubstituted benzene ring, there is a disubstituted one, and the third one is the polysubstituted benzene ring, which has more than 2 substitutions on the benzene ring. So interesting thing about the benzene and the aromatic compounds or the arene classes, that there are some of the substitution which has assigned a special name, and rather to give very detailed and a long name. So we IUPAC, these are the IUPAC accepted common names, and then they are named on the basis of these special names as a parent class. So for example, if the benzene ring has the methyl substitution, so this is termed as a toluene. So we can use a toluene as a parent name to mention that there is a benzene and there is a methyl group on it. And then we can define the other substitution if it is having other more substitution on it. And we will see that some of the examples in the next slide. Now, the cumin is if there is aromatic ring and it is having the isopropyl group attachment on it, right? So rather to write isopropyl benzene, you can write the name cumene, which is the shortest and the simplest one. Now, the styrene is basically, this is the vinyl substitution on a benzene ring. So its otherwise name is the vinyl benzene. This is also the common name. This much shorter and the convenient term we use for this is the styrene one. So if there is any substitution and you are having any of the aromatic benzene ring structure and this is linked with and substituted with the vinyl, so let's just go for the styrene one. Now, the common name and other most commonly used and very famous common names which are retained by the IUPAC system are if the aromatic ring has the hydroxyl substitution, this is named as phenol. And if it is having the amino group, so this is the aniline. If it is having the aldehydic substitution, so this is the benzaldehyde. If it is having the acetate site, so this is the benzoic acid. If it is having the methoxy group, so this is the anisole. So you may have seen some of the literature where there is the 2-hydroxybenzaldehyde or the 4-chlorobenzoic acid. So that means if we are using the benzoic acid, so that means this is the aromatic ring and this is substituted with this carboxylate site. So another thing is when we are using this aromatic ring as a prefix, this is not as a parent name, right? So then we will use the term phenyl for the benzene and for the toluene, and the toluene is the aromatic ring, the benzene ring, which is substituted with the methyl one. So if there is a CH2 next to benzene ring, so this is termed as a benzyl group. So I would take this opportunity to mention this, that the benzyl is the very stable compound when it is in the ionic form. So whenever you are comparing, we have done some of the examples in our previous lectures about the mechanism or the alkene reactions, and we have seen what was the stable carbocation. So there is a primary, secondary, and tertiary. So the tertiary and secondary carbocation is more stable than the secondary, and secondary is more stable than the primary, and the primary is more stable than the methyl one. Now, if we talk about the benzyl carbocation, so this is much stable than the tertiary one. So if in order one, so this benzyl carbocation will be more stable. So in next literature, you will see that most of the reaction are happening if this is having the CH2 there. So this is giving good reaction, number of reactions possible, which was otherwise not possible if that was a simple benzene ring. So in molecule containing other functional group, the phenyl group and its derivatives are named as a substituents. So we can see some of the example. So here you can see this is a 5-membered aliphatic side, and there is the aromatic ring. Now, which we will give the preference, and obviously we will go for the major functional group, and that is this carbonyl one. So here you have to mention this phenyl as a prefix, and we are writing this 1-phenyl because this is the first carbon with which this is get attached, and we always, when there is a joining, so we always give the lowest number and the preference to that carbon which is joining the other substitution in the hybrid or in the mixed structures where there is aliphatic and there is a cyclic chain. So this is the 1-phenyl and this is the 1-pentanone because this is basically the ketone. It is the carbonyl which is sandwiched between the two R. But right now, if we wanted to write its generic formula, so that will be the case which I have told you in the previous slide, that you can use this AR, right? And there is the C double bond O, and there is the R, right? And for more particularly, for you can use the pH as well, because pH is for the phenyl, right? Because right now this is not the substituted one. This is not the general benzene ring structure with any of the substitution. This is only the aromatic benzene ring. So we can use the pH, and there is a carbonyl, and there is the R, which is just a aliphatic R group, right? So the second example is for there is a methoxy on this aromatic ring, right? And there is the four-member ring stuck, four-member aliphatic, and there is a carbonyl one, right? And you can see that this is again the ketone one, but right now there is aromatic ring which has a substitution one. So how we will name that one? Because we are using this aromatic as a prefix, so we also have to mention that at which it is not a simple aromatic benzene ring. It has some of the substitution. So we will write this one. For example, this is the one for this is the first carbon. We have to assign the lowest number to the major functional group. So this is the 1, 2, 3, and 4, right? So at the fourth carbon, then there is the phenyl. We have written this phenyl, but this phenyl is again having a substitution. So we have to see at what position this substitution is and what that substitution is. So 1, 2, and 3. So there is a third position, and there's a methoxy, right? So this is a methoxyphenyl. And here this is the four carbon chain, and you can mention this is a second carbon where there is a carbon in one. So this is the 4,3 methoxyphenyl 2 butanone. Now the next one is the this is the again the four carbon chain structure, which is the longest chain here, right? Another one is the ring structure, which is the pH, which is the aromatic one. So we will take it as a prefix one. And now here, this is the second carbon on which this is a double bond, and this is the second carbon on which the phenyl group is attached. So the 2-phenyl and 2-butene. Now, this Z is basically to represent that this structure is in a cis conformation, right? Though this is a separate topic, but for your understanding, let me write this one for you, that this Z and E conformation is for cis and trans, and that is applicable for the double bonded compounds. So you have to compare if the both of the bulky group are on the sharing the same plane or sharing the same side. So then that is a cis, and we will use the Z for the zoosamin and E for the antication. So the trans is for E, because cis trans was the more trivial way or the classic way to name that one, but eventually that was updated in terms of the Z and E transformation rather to write the cis and trans. So the Z is for the cis, and here you can see that in this double bonding, this is the double bond, right? And here this is the methyl group, CH3, right? This is a CH3. This is the CH3, right? And here this is the H on this carbon, right? So if you just compare these one, so from this side, the phenyl is the most heavy and the methyl is the smaller one. And if we compare this one, hydrogen is the smaller one and the methyl is the heavy one. So now you have to compare, either you can compare the both of the, you can see both of the bulky side, or either you can see both of the lighter side. So here you can see that in this double bonded carbons, you can see this the methyl, and this is a smaller one, right, on this side. So the both lighter group of atoms or the substitutions are sharing the same plane or same side. And same is that both of the bulky are on the same side. So that's why this is the cis conformation, and that's why we have written it as a Z, because that is important to mention when we are drawing in the double bond. And if that is asked to you, that you have to mention their configuration as well. So you should write that either that is a Z and E. Otherwise, in just the normal case, you can even draw that and simply name that one without mentioning their spatial configuration, that either that is cis or trans. Now the next is the disubstituted benzene. So when two substituents occurs on a benzene ring, three constitutional isomers are possible. The substituents may be located by numbering the atom of the ring, or by using the locator ortho, meta, and para. So the both are equally important and usable naming in case of the arenes and the benzene compounds. Um, so you should know that what the para, meta, and ortho refers to. So the very first, the main reference or the substitution position is taken as a first position always on a cyclic structure, because in a ring structure every position is equal unless there is other substitutions which are deciding that which one will be on the preference and which were the later one. So the metal, any of the major functionality which it has assigned a special name, so you can take it as a reference at the first position, and the second position will be the ortho. Like in this case, this is a nitro, this carboxylate is our main one, so this is the benzoic acid, right? And if there is a second position on a nitro, so this is the 2-nitrobenzoic acid, or you can write the ortho nitrobenzoic acid. So the ortho are all easily are also the IUPAC accepted one and the retained naming for the aromatic compounds. But if you are asked to write the IUPAC name, so you will prefer to write their position unless that has been asked or mentioned that you should go for the ortho, meta, or para equivalent naming for these one. So the second is, if this is the second substitution on third position, so this refer to the meta position, and that is the 3-chloroaniline. And the fourth position referred to para position, and here you can see this is a 4-bromotoluene. Now when there is the 2-methyl group on aromatic, so we use the special name xylene for mentioning that there is aromatic benzene ring, and this is substituted by the 2-methyl group. But obviously, by writing this meta, ortho, or para, you are specifying that where this second substitution is, either that is on the first position, second, or the third one. That makes sense? So let me write for you another thing that it will be easier for you to compare this one. Like this is our reference position, right? And from the reference, which is the first position, you have to see that this is the ortho, this is the ortho, this is meta, this is meta, and this is the para one, right? Because other sides are the equivalent one unless there are the fixed positions or the substitutions which are already available. Now we can see the other examples, and here this is which is not given any of the special name, so you have to mention their position and the substitution names as we do the naming of the all of the compounds in the IUPAC naming. So if there are the two different substitutions, then you have to number them and name them on the alphabetical ranking, right? So here you can see this is a Cl and there is ethyl. So a Cl has a preference alphabetically as compared to the ethyl one. So we will start numbering from this side. So this is 1, 2, 3, and 4. And in the naming, we will write this is a 1-chloro-4-ethyl benzene, or either you can write the para-chloro ethyl benzene. This is a common name, or in the way of the orthometa and paranaming structure. So the another example is that there is a Br and there is a nitro. So obviously bromine will get the preference alphabetically. So we will name it as 1-bromo-2-nitrobenzene, and this is ortho-bromo-nitrobenzene. Now the third example is where there are the same substitutions. So there is, you can start numbering from any of the nitro side, because in a cyclic ring, this is all the same one. So here you can either write 1, 2, 3 or 1, 2, 3. So this is the 1,3-dinitrobenzene or meta-dinitrobenzene. So it will always take the first substitution as at the first position, and that will be relative to that first position, that either that is on a meta, para, or the ortho, or the second, third, or the fourth one. Now, the next is the polysubstituted benzene structures. So where there are the more substitutions, more than three, or the three or more substitutions on the aromatic rings, and then they are grouped as a polysubstituted benzenes. So again, you have to mention their names by on the alphabetical order, and you will number these one for naming, and there will be the numerals for mentioning their position. So if they are given, any of the substitution has a special name, so we will take it as a parent name. But if there is no special name associated with that substitution, then we will mention it in with their position and alphabetical order. So we can compare these three examples. So the very first example is, if you just look at this one, Cl at the aromatic, nitro is substituted on the benzene ring, and the methyl on the benzene ring. So we know that the nitro and the chlorine has not assigned any of the special name. Rather, the methyl substitution on the benzene ring has the toluene. So we will use the toluene as a parent compound name, right? And we can write the rest of the substitution positions. So here, this is the first, then second, third, and fourth. And obviously, I can't go from go for the numbering from this side, because then this will give the highest number to the substitution, and we always have to give the preference to the substitution and to assign the lowest number to the substitution. So that's why I'm moving towards the direction of my right side at the clockwise direction to number these substitutions. So this is the 4-chloro, 2-nitro, toluene, right? So that may be um, confusing for you, and you may be asked the question that we didn't do this previously, because there was only the two substitution and we were writing on the basis of their alphabetical order. But right now our preference was the methyl group, right? So accordingly, to assign the lowest number to the substitution, so Cl is alphabetically on the priority, but we cannot go for this side of the numbering. So that's why the Cl is getting the higher number, right? But we will write in a naming it first. It will mention it earlier on the first, then the nitro one, but it is getting the higher number because in the order of assigning the lowest number to the substitution. I hope that makes sense and you are understandable and you're getting my point. So the second one is where there is a OH, and we know the hydroxyl substitution on the benzene ring termed as the phenol. So we will use that phenol as a parent name. And there are the three same um, atom or the group of atoms substitutions attached to the benzene ring. So these are the bromine. So we will just separate these one by their position and using the prefixes tri, di, if they are repeating the same substitution. So here there is a case, this is the 2,4,6 tribromo, right? Phenol. Now the third is example where we can see the nitro, Br, and the ethyl. They are not associated with any of the special names. So for that case, we have to name these according to their priority, right? And we will number these one in that way. So here, this is a case that from which side we should start numbering, right? I can go for in between. So obviously from the one side, I have to pick from which numbering side I should choose for the numbering. So for example, BR, though this is alphabetically on the priority, but this is in between the ethyl and the nitro one. So I have to go for any of the side. This is a nitro and this is ethyl. So the ethyl has the preference over the nitro alphabetically. So I will number from this one as a 1, then second, third, and fourth. This is the preferred side to assign the lowest number to the substitutions. So that's why the 2 bromo, 1 ethyl, 4 nitrobenzene. But when I'm writing the name, right, though the numerals could be the different one, but I will write that substitution first, which is getting the alphabetical preference, right? So Br is on the alphabetical preference. So there is a 2 bromo, 1 ethyl, 4 nitrobenzene. Now at the last, there is a task for you. And here I have mentioned the 4 substituted and the mixed aromatic or the benzene analogs, and you have to write their name according to IUPAC name. So by mentioning the positions and the numerals, but of course, where there is possible, you will use their special name system. So here there is a hint for the second and the C, because this was a little bit tricky and challenging for you if you just have started to naming the benzene derivatives or the benzene based structures. So for the B, there is a term that whenever we were talking about the IUPAC naming, and since we just have completed the rest of the hydrocarbons, so they were just made up of on the main uh, frame, main structural frame, that was the carbon hydrogen base, right? So we always go for the longest chain. So once there is no the carbon and there is any of the atom, that is a sulfur, oxygen, and nitrogen, so it means this is breaking that longest carbon chain. So then that position will not be counted in the longest chain. So then that substitution you has to mention by writing that element, that this is attached to this atom. So for example, there is N. So wherever we are mentioning the substitution, that for example, there is a phenyl group attached to this one. So we will write N phenyl to mention that this phenyl group is attached to the N, because right now we not just can't mention the position of the carbon, because this is not attached to the carbon. There is a heteroatom, and this is the breaking the longest chain. So there is no that doesn't make any sense that if you can assign the number to this one, because if you'll just write a number, so that will be assumed that this was the carbon chain. That makes sense. So here we need to mention that heteroatom as a substitution or as a position, which we're using as a numeral number to mention that position. So for the C, right? So another thing which I wanted to mention, because here this is the N and this is attached to the carbonyl one. So this functionality is termed as the amide one. And if you wanted to refresh your information about the functional group and their generic formulas and what the class names, the suffix we use for naming these classes of the compounds. So just check out my lecture on the function group and the classification of the organic compounds. So the C1, for the hint for the C is that when the carbonyl is attached on the aromatic one, right? So this is termed as the benzoyl. We have seen was the benzyl when there was aromatic and this was attached with CH2. So if this is with the carbonyl one, so then we will write it as a benzoyl. So you have to name that, keeping these points in your mind. So that is your task, and you can submit that on a Moodle, and you can comment on the video lecture. So I'll be happy to answer your queries and to confirm either you are writing or naming that compound correctly. Take care. Have a good day.